My name is Kirill Malkin. My duty is to save money on data storage. And I do that as Director of Engineering at Hewlett-Packard Enterprise, HPE, focusing on HPC Data Management and Storage. So today we're going to talk about data movement and tiering. So why move data in the first place? Well, because wouldn't it be nice if we could keep everything in DRAM, right? But that's not possible. I mean, the world would have been really simple in that scenario. But the reality of it is that DRAM is volatile and it is expensive. So what we do is we move data to a non-volatile tier, and we also don't have that many choices for that. I mean, really, there's just only two choices. It's solid state or magnetic. I mean, there's no other technology that's out there. I mean, there's something that's coming up, but it's far from productive state. We also like to make copies so that we can, because we don't trust the media. We don't trust ourselves. We don't trust the software. And we like to make copies. We call them differently. It could be snapshots, backup, archive, what have you. Every time we move the data to a less expensive medium, it's called tiering, basically. So we typically go from solid state, from memory, obviously, from solid state to hard disk, to cloud, to tape. And we also need to move data sometimes because of the locality. It could be different computer system. It could be different location. It could be different organization. And it could also be computing at edge, which is a new trend that we're going to touch on a little bit. So doing this properly requires data management. So let's talk a little bit about pushing computing to edge. I mean, I know that this group has been pushing computing to edge in a slightly different way for a long, long time. But we're talking now about actually moving compute closer to where the data is, right? I mean, and this is happening because transferring the data is expensive. In the amounts that are created by modern IoT technologies is just too much data. And another reason for that is that decisions need to be made at the edge sometimes. I mean, we just don't have the time to send all that data over somewhere and make decisions on that. So, and this is applicable for all applications, AI, big data, and as well as HPC. So more and more mini data centers, if you will, are popping up at the edge. So what happens with the data and the results of the processing that occurs at the edge? Well, some of the IoT data is very valuable. I mean, think about self-driving cars and technologies like that. It's important to keep all that data because it could be very expensive to reproduce. Results could be also need to be preserved typically. And this means moving it to another location or possibly multiple locations if we want to share that data with other organizations. So the key to doing this in an organized way is to rely on metadata. Because in order for us to understand what we need to move, we need to first look at what are we moving, right? And where the data is and how to find it. And then based on that information, we can create what we call data sets and then perform the data movement in the direction that we need to go. So in talking about the access methods, which I was asked to kind of comment on, POSIX, we all believe, I think, in this room, is still the dominant access method in HPC. Typically, it's not 100% compliant, but it's pretty close to that. It's what I would call consistency optimized POSIX. This is because there's significant dependency of the HPC codes on the POSIX semantics. Non-HPC applications tend to go, to store data differently, and they go into technologies that I would call buckets of objects in the cloud, right, or also known as S3 API. And then there's also emergence of data lakes, which is key value store-based technologies. But when we talk about the POSIX, moving POSIX data is actually better done in what I would call dormant form, where the data is immutable, where the data is not changing. And then once the data is moved to the destination location, then you can actually stage it into POSIX and compute on it. So data management, what challenges would it solve? First of all, it's too much data. And if you have 1 petabyte of data, you have too much data. You probably need a way to find a cheaper method to store it. Another one is too many files. Where are my files? I mean, there was a lot of discussion in the last day about how do I tell where my data is? How do I move it to the place where it belongs, and so on? So locating and constructing data sets based on metadata is important. And another one is need for speed. Some workflows require high performance storage. And it's everywhere. It's an HPC in data analytics as well as machine learning. There's need for faster storage. So focusing a little bit more on the data management framework. This is a kind of ecosystem that, for tying together high-performance storage and the back-end tier. The high-performance storage is active tier where the data is hot, where the data is produced, worked on, computed on. So that's where the performance is. And the method of storage could be different, but it's POSIX-like. And the back-end is a dormant tier. That's where the data goes to sleep. That's where it's cold and it's easy to move. That's where it's capacity optimized. So what DMF does is ties those two together. So what exactly is DMF? DMF is a data management hub that allows you to encompass the entire data life cycle. It is also a policy-driven data movement and tiering solution for a variety of different backends that are cost-optimized. It's also a scalable metadata search and capture engine. And that's new in DMF. And it's based on big data technology that we brought about as part of re-architecting DMF. And finally, it's a scalable parallel data transfer engine. A couple of words about DMF. DMF has been around for quite some time. So the DMF used to be called Data Migration Facility, was introduced sometime in the 80s. And there's a lot of users of DMF in this room. It stores, I would say, probably over exabyte of data today and continues to go very strong. But we decided to re-architect this technology to move it another 25 to 30 years forward by basing it on new technologies that are available today, and most importantly, focusing on metadata processing. And that's how Data Management Framework was created. And the current version of that is distributed as part of DMF suite products of HPE. Is DMF suite version 7.1. So what can DMF do? Well, first, most importantly, it maintains namespace reflection. So it allows to actually know what is inside the namespace. And it provides essentially all metadata ability to search and query metadata of the file system that it manages, It actually allows to also transparently migrate and recall files. And what that means that you can actually see all the files in directories, and you will be able to open the file, and the DMF will bring the file from the backend into the front end file system and let you access it and delay the application until the data is available. It also, especially with DMF 7, it allows staging and destaging the data, the files and directories, which allows us to be independent of the file system completely and manage simultaneously multiple file systems. It also allows us to recover files and directories and entire file systems, effectively replacing backup. If you think about it, this is very powerful because you can store the data in the dormant form without any file system whatsoever, without any access, and then in a very controlled way, stage the data into a variety of namespaces that you can create either on demand dynamically, or you can have a static namespace where you just stage parts of your backend data. And that can be done in a very organized way. You can construct and manage data sets based on file and directory metadata, which includes also extended attributes. You can stage data sets just in time, for via API or HPC job scheduler call, for example. I'm going to have to go a little faster here. So one important point that I wanted to stress is the extensible metadata support. So this, extended attributes have been with the file systems for a very long time, but they haven't been used all that much because it's difficult to search on them. But once you have namespace reflection inside a scalable distributed database, essentially big data database, then you can perform very efficient queries and construct data sets based not just only on file location inside the path, but also on based on variety of metadata. I mean, it could be user or group that the file belongs to. It could be size of the file, which could be important in some policies, and it could also be extended attributes. So you can assign extended attributes using simple set of at or POSIX command. You can actually assign multiple extended attributes and then perform data set construction based on that data. And then you can essentially perform movement of data in a variety of ways. You can send the data to the backend. You can send the data to different front-end file systems and essentially organize your data based on your metadata content. And of course, the DMF has always supported transitioning to new storage technology. So we've gone through 8 generations of LTO. The only way to preserve data and make sure that you can access the data is actually moving it to the newer and newer storage technology. And that's what DMF has done in the background for a very long time, and we continue to do that going forward. A couple words about architecture. So DMF7 is entirely architected based on big data technology. If you're dealing with a lot of metadata and you're talking about billions and possibly tens and hundreds of billions of files or objects, every time you deal with something like that, you need big data technologies. So we've created a framework which is completely containerized that is essentially bringing big data technology into DMF7. And policy engine is, so database is based on Cassandra, policy engine is based on Spark, and we kept the data movers, we brought them from previous versions, because this is what's been working really, really well about DMF. It's been running for a couple of decades, and it's worked really well. One point to stress here is that DMF7 now allows plugging any type of a file system. So it's designed to be unified from the front-end side. So currently it supports Lustre and HPE XFS. It will support GPFS. It will support other file systems as well. And management of the data and data sets in the backend is completely unified, and so is the CLI. So regardless of the front-end file system that you're using, your overall interface with the system and API continues to be the same. We've excelled at tape for many years. I'm not going to go into that. Zero-watt storage is a very interesting technology that we've introduced where we look at disks as a tape. Remember, magnetic media, whether it's spinning or it's just moving, I mean, it's the same magnetic media. So we felt like we can store data very efficiently on individual disks if we think about them as tape cartridges. Solution scales very well because it's all based on big data. We can scale database nodes. We can scale data movers. This is an example of design for a Lustre Tering, a very simple kind of a Lustre file system on the left side and object storage on the right side. And we perform tiering, staging, destaging, everything that I talked about in this environment. This is just a graph that shows that we achieved the target performance with that. Very nice distribution across parallel movers. So in the summary, I'd like to mention that DMF7 supports tiered storage. It allows you to do scalable storage, tiering, and backups. It supports high latency media such as tape and disk and cloud very, very well. We're looking to support Glacier actually at some point soon, natively. We also really improved our metadata search technology, and we can locate, scale, select, and move large amounts of data based on metadata, including extended attributes. And we can also support moving the data or bursting them into high-performance storage. With that, I'd like to thank you, and I don't know if there are any questions.